Chapter 1 is all about preliminaries, and the first subtitle that we have is physical quantities and units of measurement. Okay, so when we start with the word physics comes from the Greek word meaning nature. So physics is one of the core science fields that deals with energy and matter, the relation between energy and matter. There are equations that we connect them together and describe the energy and how the matter, the different types of matters are related with the amount of energy and their interaction. Okay, so today physics is treated as a base for science and have various application and to make life easy. So apart from this, the knowledge of physics plays a very significant role for technological advancement. So science will do some investigation and produce results. Then that result will be used for technological advancement. So the development, engineering, and technology of nation. So physics is a science of measurement. So measurement consists of comparison of a known quantity with a known or fixed quantity. That's why whenever we say measurement, we have to see the different measuring instruments also. So the quantity used as a standard of measurement is called unit. The scope of physics is very wide. It covers mechanics, optics, to name a few, and this, oscillation, heat, thermodynamics. One will be included on the other. Okay, now currently the following new subjects related to physics are developed, like biophysics, chemical physics. So the boundary between those two different subjects is removed and are away or from physics, and the other from like biology, chemistry, and they combine with the scientific investigation results from physics and they produce the different results. Okay, so having this in mind, now let's continue to the physics. It's known that it is an experimental science. Experiments require measurement, and we generally use numbers to describe the results of measurement. So having this in mind, in the first subtitle, we have physical quantities. So any number that is used to describe physical phenomena quantitatively is called physical quantity. So this is the expression of physical quantity. Physical quantity is quantifiable property. Quantifiable property ascribed to a particular phenomenon or a body. For instance, the length of a given rod, or the mass of a given body, or the time interval of a certain vehicle from to arrive from A to B, and so on. They are needs a quantifiable property, so they are called physical quantity. Okay, so there are two types of physical quantity. One is basic, or we can say fundamental or primary physical quantity. The other is derived. So in basic, they are called independent quantities. They are quantities which cannot be expressed in terms of any other physical quantity. So there are 7 fundamental physical quantity. One is length, the other is mass, the other is time, electric current, temperature, luminous intensity. Whenever you say luminous intensity, is the quantity of visible light that is emitted in unit time per unit angle, so amount of substance. All these are considered to be the 7 or basic or fundamental or primary physical quantity. Okay, next to that, now let's see the basic fundamental physical quantity with derived quantity. So this is from day-to-day practical application. The basic quantity is considered to be this one. This is the brick. So the combination of this basic quantity or fundamental physical quantity, they will produce a derived physical quantity, and is like a house, which is a combination of one is brick, there are also cement and other ingredients will be used to build this house. But this one, the ingredients or the fundamentals building blocks are considered to be or related to those of the basic quantities or fundamental physical quantities. So we can relate this one to the derived physical quantity. Okay, so having this in mind, now let's see derived or secondary physical quantity. They are also called independent quantities. They are quantities that can be expressed in terms of fundamental quantities. Example, we have speed, acceleration, volume, and rho can be, for example, speed can be derived from distance, which is measured in meter, over time, which is measured. So the distance or the length of something is included under basic or fundamental quantity, and the time is also one of the 7 fundamental physical quantities. The combination of the two will produce speed. Okay, now let's go to the one. We define physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. So this is a way by looking at how they are calculated, it's possible to define the physical quantity. The other thing, measurements of physical quantities are expressed in terms of units, which are standardized values. Without standardized units, it will be extremely difficult for scientists to express and compare measured values in a meaningful way. So for this, we need to have standardized units. The standardized units will be operated in different countries, so different in the world, so they will have the same standardized quantities. So one country will fabricate certain instruments with these standardized units, and the other country is possible based on the standardization they can operate or they can use for different application. Okay, so the other one, the second one, is regarding the SI units for basic and derived units. So in first General Conference on Weights Measurement held in 1971 adopted 7 base or fundamental units, the units form of the SI system. So the name SI is an abbreviation for International System of Unit. Most of the time we say SI unit, SI unit, SI unit. So this means International System of Units. So the SI units along with their symbol are given in the table below. This is the table which have the 7 fundamental physical quantities: length, mass, time, electric current, temperature, luminosity, amount of substance are included under the 7 fundamental physical quantities, and these are the units. The first one is for meter, the second one is kilogram, the third one is second, and ampere, Kelvin for temperature, luminous intensity, candle, amount of substance, more. So these are the symbol. The symbol for meter, in most cases we use small m. Kilogram can be written like this, kg. Second, s, or sometimes c, ampere, a, and Kelvin, k. Candela, cd, mole, the amount of substance, the unit is mole, and sometimes we write like this one. Okay, so these basic quantities and these units, sometimes the dimension can be represented by, the length can be represented by L, mass can be represented by time, it's possible to represent by T, and temperature with theta. So these are the dimensions. So there is some variation that you get in a different book. So the luminous intensity, the symbol is F. The electric current is I. Sometimes we use small I is also possible. For example, if the current can be written as a function of T, so we can use small I. Under brace we write T, so this is equal to like 2t squared plus 3t plus 5, and so on. Okay, so having this in mind, so we have derived units obtained by combining these basic units, as I told you before. So the derived can be a combination of different basic units. The 7 fundamental, combining these 7 fundamental physical quantities, you can produce the derived unit. For example, combination of units of length and time gives us a derived unit, which is speed, and the unit is meter per second. So this is for length, this is for time. Some drive units are following in the table. Here is the table. For example, you can take a force. The unit is Newton, so the force is a combination of the fundamental physical quantity. The first one is kg, which is mass, and this one is length, meter, and this one is indication of the time, which is second square. The other one is speed, pressure, which is measured in Pascal, force per unit area. The force is already written, and the whole combination will produce with the area kg m the power of -1, or kg divided by kg over meter second square. Can describe the Pascal, because the force is kg m square over area is measured in meter square. Meter cancelled by meter, we have m the power of -1 is as it is, -2. So this is representation for pressure. Just like that, we have also for energy and for power. Okay, let's start from conversion units. So when you start to convert a quantity from one unit to another, multiply by a conversion factor. For example, if you want to get the value in centimeter, if you have 20 millimeter, then in order to get it into a centimeter, so you have to divide by 10. That is a conversion factor. 20 millimeter divided by 10 is equal to 2 centimeter. Okay, so to convert a quantity from one unit to another, multiply by the conversion factors in such a way that you cancel units you want to get rid of and introduce the unit you want to end up with. You want to end up with centimeter, and you want to get rid of millimeter, like 20 millimeter. So 20 millimeter multiplied by 1 over 10, or multiplied by 0.1. So 20 millimeter multiplied by 0.1. Finally, you will end up with meter. So the millimeter will be removed. Here is an example unit conversion. These are the quantity, and you want to convert from inch to meter. Then this is the operation. For example, we have inch. So we want to convert the inch into meter, so we have to multiply that inch by 0.0254. This is the conversion factor. And there is also a foot, so we want to convert into meter, so multiply the foot by 0.3048. This is the conversion factor. Finally, we'll end up the unit into meter. Okay, so for example, if you have 100 inch and you want to know how much in meter, so multiply 100 by 0.0254, and it will become 2.54 in meter. Just like that, you have for length, for mass also, we have pound, and I want to convert into kilogram. We have to multiply pound by 0.4536, and you will get into kilogram. Metric ton, to multiply this one on this one is by 0.02835, and volume in meter cubed, later multiplied by 0.001, and gallon when to convert into meter cubed, so multiply by 0.00379. These are the conversion factors. Okay, the other thing, conversion of temperature Fahrenheit into Kelvin. So first you have to have this one, Fahrenheit. The Fahrenheit, it may be 32 degree Fahrenheit. If you have 32 degree Fahrenheit, 32 minus 32 becomes 0, multiplied by 5 over 9 become 0, is equal to 32 degree Fahrenheit will be equal to 273.15 degree Kelvin. The other one is if you want to convert from degree Celsius to Kelvin again, so the Celsius plus 273.15 is equal to degree Kelvin. So this is the way of converting Fahrenheit into degree Celsius into degree Kelvin. So if you have degree Celsius, just add 273.15, you'll get into Kelvin. Okay. Okay, the next slide is regarding answer 1.2, uncertainty in measurement and significant digits. You know that most measurement in the lab, physics is experimental, so by itself. So there is uncertainty in during the measurement in the laboratory. Measurements always have uncertainty. It's very clear. So for instance, if you measure the thickness of your handbook using an ordinary ruler, result will be 3 millimeter. Let's say the result is 3 millimeter. Okay, it will be wrong to state that this result is 3.00 millimeter because the measuring instrument do not have the ability to measure after this point. So it measures with ordinary ruler, measures though the minimum measurement from the ordinary ruler is 1 millimeter. We don't have 0.00 millimeter, we don't have 0.01, we don't have 0.10. So whenever we write report, it's not allowed to write like report after measuring of that thickness using ordinary ruler. So it's not allowed the report to have 3.00 millimeter. So given the limitation of measuring devices, because of the limitation of this ordinary device, this doesn't mean that there are other instruments that measure precisely. Okay, now you can't tell whether the actual thickness is 3.00 millimeter or 2.85 millimeter or 3.11 millimeter by having this ordinary ruler, because this ordinary ruler has only 1 millimeter. So the minimum measuring value, or the minimum that we get from this ordinary result, is 1 millimeter. So we don't get this 0.11 or 0.01 or 0.1. Okay, so but if you use micrometer caliper, a device that measures distance reliably to the nearest 0.0, so it can have this much, the smallest value of this micrometer caliper can be 0.01 millimeter. The result will be it's possible to report like 2.91 millimeter. So the distinction between the measurement with a ruler and with a caliper is in their uncertainty. So the measurement with a caliper has smaller uncertainty as you compare with the measurement with ordinary ruler. So this one, the caliper, is much better than the ordinary ruler. So this caliper help us to measure after a certain digits after this point. Okay. So the uncertainty is also called the error because it indicates the maximum difference there is likely to be between measured value and the true value. Now let's proceed to the next. So the uncertainty error. So based on this one, we have a division like this one. The table shows the instrument. So before we see the different systematic error like random error. Now let's see the instrument with range of measurement in their accuracy. Now let's start from the measuring tape. This actually used in construction or retailer or in different places. So in this case, this has a range of measurement. It can measure, the instrument can measure from 0 up to 5 meters. This is the range of this instrument, but the accuracy is 0.1. Now the minimum measurement is 0.1 centimeter. Now meter ruler, this is found in the laboratory. So the meter ruler can measure from 0 to 1 meter. And again, just like the previous previous one, the minimum value is 0.1 centimeter, but Vernier caliper can measure from 0 to 15 centimeter. So which is less than these two. This is up to 5 meters, this is up to 1 meter, but this is up to 50 centimeters. But the accuracy is much better than the previous one. It can measure 0.01. The minimum measurement that we have from this Vernier caliper is 0.01 centimeter, which is much better. So micrometer screw gauge from 0 to 2.5 centimeter. Actually, there are some advancements on these two instruments, and the minimum accuracy, just to show you, the minimum accuracy is 0.01 millimeter. So You see, these are the vernal caliper that we have. This is micrometer screw gauge. As you can see here, it can goes from 0 up to this value, from 0 up to this value, which is 2.5 centimeter or 25 millimeter. And this is the minimum that we have, 0.01. It's an indication here. So there is steps for measuring this one, and other videos I will show you how to use this vernal caliper and this micrometer. Okay, now let's proceed. So the next one is regarding if the diameter of steel rod is given as 56.47 and which is plus or minus 0.02 millimeter. This means that now we are going to interpret this one for the diameter of steel rod, which is measured 56.47 plus or minus 0.02 millimeter. This means that the true value is likely to be within the range of 56.45, which means 56.47 minus 0.02. So when you subtract 0.02 from this number, you'll get 56.4745 millimeter. And when you add this one, 0.02 into this one, it becomes 56.49. So 56.49 millimeter. Commonly used shorthand notation, the number 1.6454 means that this is 1.6454 plus or minus 0.0021. So we have to count these digits. So 1, 2, 3, 4. So 0.0021. So the number, this one actually shows this is a range. So you subtract this one and you add just like the previous one. Okay, so having this generally errors fall into two categories: random and systematic. First one is systematic error resulting from measuring devices. So here in systematic error, you are to consider the measuring device being out of calibration. If you don't calibrate measuring instruments, in some time interval, then you will face error, and that error is systematic error. So this error can be eliminated or minimized by using appropriate measuring device, and pre-calibration is very important. So sometimes the device may measure above the expected or below the expected. That will be very difficult. So the other one is random errors resulting from fluctuation of measurements of the same quantity above the average. So the measurements are equally probable of being too large or too small. These errors generally result from fineness of scale deviation in measuring device. Some are very fine, so they will have a very large division from 0 to 1. There may be 20 divisions. There may be from 0 to 1. There may be 100 divisions. There may be 1,000 divisions. So if it is 1,000 division, it's very fine. So the fineness is good. If it is 20 divisions, so it's not fine. If you compare to the 100 division from 0 to 1. So that is the errors that you face because of the fluctuation of measurement is called random error. Okay, so there is a systematic error are generally simple to analyze, but random errors require more careful analysis. So systematic is very simple to analyze because it is a result from measuring device because of out of the calibration. Okay, so this is an example of the errors that we have. The correct value is 8.3 centimeter that we read, but one person to the left side or the other person to the right side. The left side reads 8.2 centimeter. The right side read 8.5 centimeter. So the correct one is 8. So this is also an error. So in laboratory, there is a personal error. This is an example of personal error that we face. Okay. So there is a statistical method for calculating random uncertainties in measurement. The following rule used to determine uncertainty in a single measurement when using scale or digital measuring device. Now, let's find first the uncertainty in scale division measuring device like meter sticks. The smallest here in the uncertainty can be calculated for this one for meter stick or others without the digital measuring device. So this can be calculated as the smallest, we consider the smallest increment divided by 2. For example, for meter stick, the smallest increment is 1 millimeter. Smallest increment is 1 millimeter. So we have 1 millimeter from 0 to 1 centimeter, we have 10 division. So because the smallest increment is 1 millimeter, so 1 millimeter divided by 2, so we get the uncertainty. So after we get this uncertainty, which is 0.05 millimeter, this into, when we convert this into centimeter divided by 10, it becomes 0.05 centimeter. So whenever you write the result, if you measure 10 centimeter, you have to write 10 centimeter plus or minus 0.05 centimeter. You have to add the uncertainty. So we are uncertain with this margin. So our measurement may be 10 plus 0.05 centimeter or 10 minus 0.05 centimeter. Okay, the other one is uncertainty in digital measuring devices equal to the smallest increment. So uncertainty in digital measuring device equal to the smallest increment. So the smallest increment is this one. So reading from digital balance, digital device, for example, is 5.7513 kilogram. Therefore, sigma x is equal to 0.01. For this, the smallest increment is 0.000. This we will have to take the last one 1. If this number is 5.751, the smallest increment is 0.001. If this number is 5, if the digital balance reads 5.75 only, so the smallest increment is 0.01 only. So in this case, the uncertainty is this number. Therefore, whenever we write report, we have to say that 5.7513 plus 0.001 or 5.7513 minus 0.001. This is how you are going to report. So in general, any measurement can be stated in the following preferred form, that is, measurement is equal to the best measurement plus or minus the uncertainty. So this is the best estimated estimate measurement plus the uncertainty. Okay, so the other topics that we have is significant digits. Here we have a rule. So before the rule, we have to know how we consider this significant. When you measure lengths of certain objects, line as 6.8 centimeter, digit 6 is certain, while 8 is uncertain. After a point, we have 8 uncertain as little or less more than 0.8 centimeter is reported as 0.8 centimeter. Plus, normally those digits in measurements that are known with certain length plus the first uncertain digits are called significant figures. Thus, there are two significant digit figures in this one. So whenever you ask to find the number of significant digits, so we have two significant digits, or we can say significant figures. Okay, so the number of significant digits in any quantity depends upon the accuracy of measuring the instrument. If the instrument is more accurate, so we have a very large number of maybe significant per figure, maybe. So more the number of significant numbers of figures, less is the percentage of error. You know the relation. So we have after a point, for example, we may have 4 number, 5 number, blah blah, like that. Measurement of quantity. If there are less number of significant figure measurement, more will be the percentage of error. So the number of significant of a quantity may be found by the following rules. Rule number 1: all non-zero digits are significant. For example, if you have 315.5, these are non-zero digits. So the number of significant figures here is 1, 2, 3, 4, 5. If it is 15.58, it is 4, 1, 2, 3, 4. If it is only 315, it is 1, 2, 3 only. So these are how the first rule that we have. All non-zero digits are significant. For the second rule, all zeros between two non-zero digits are also significant. For example, these are two zeros between these two non-zero digits. This is the other zero between these two non-zero digits. So this is also two zeros between non-zero digits. In this case, we have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in general, this one has 10 significant figures because all zeros between two numbers. For example, if you have 2, 0, 5, so we have 3 significant zero will be counted. So we have 3 significant. If you have 2, 0, 5.01, so here we have 5 significant figures. So in general, the second rule expressed as all zeros between two numbers, two non-zero digits are significant. Okay, the third one is all zeros which are to be to the right of decimal point and also to the right of non-zero digits are significant. For example, 50.0 has 50, which we have 5000, so this will be counted, and then we have 2, 3, and 4 significant figures. If you have 1.00, we have 3 significant figures. If you have 15.00, this also has 4 significant figures. And if you consider this one, we have 0.04050. Here 0 will not be taken under consideration, so we have 1, 2, 3, 4. There are 4 significant figures. There are 4 significant. This will not be counted. This will not be counted, but this 0 will be counted. Okay, so let's continue with example and other rule.